Today, we are going to see proportional control. Proportional control or P control or P only control. Yesterday, we have seen on-off controller. On-off controller. The drawback in this on-off controller is it is wandering around set point. The process variable is wandering. Process variable is wandering around the set point. That is the drawback with the on-off controller. Second problem is it has fatigue failure. Fatigue failure may happen because frequent on-off. To reduce this fatigue failure, we introduced a bandwidth. The third problem with on-off controller is chattering. These three problems were there in on-off controller. We can reduce these two. We cannot avoid, but we can reduce these two by introducing a differential gap. On-off controller with the differential gap. So this is ideal on-off controller. If error is error versus controller output. If you plot, this is the characteristics of on-off controller. If error is positive, on. If error is negative, off. The problem here is, if the error is switching between positive and negative, sometimes it may happen. Yesterday we have seen an example. Switching between positive and negative, the controller will switch between on and off. That is called chattering problem. To avoid that, we modified the characteristics with a differential gap. Suppose 2% tolerance we are giving means, the tolerance is 2% means, suppose 60 degrees centigrade is the set point means, you can have a tolerance of 2%, 2 degree centigrade, that is 58 and 62. If within the tolerance, you can operate, then you can reduce this chattering as well as fatigue failure. If it exceeds 62, it will turn off. The controller will be turned off. Up to this is on. Up to this is on. Here it is turned off, but there will be a further increase. When it falls below this 58, then only again it will be turned on. So that the frequent on-off can be reduced. Differential gap. This is called differential gap. Or we can say that on-off controller with hysteresis. This area is called hysteresis. On-off controller with hysteresis or differential gap we introduced. Chattering is removed. But fatigue failure reduced. But the magnitude of wandering increases. Magnitude of wandering increased. To reduce that, we can go for 3-point controller. We can go for 3-point controller. On-off controller is 2-point controller. What are the 2 points? On, off, only 2 points. On means 100% output. Off means 0% output. Only 2 points. Now it will approach. If the error is minus 10, minus 12, minus 15 like that. That is less than minus 10 means 0%. It is greater than minus 10, but less than minus 5% means 28% output. Between minus 5% and plus 10% means 50% output. 50% output. Between 5% and 10% error means we are giving 78% output. Above 10% means 100% output. If the error is above 10% error means 100% output. Now the set point is 60 degree centigrade. Now 30 degree centigrade at room temperature. Error is above 10%. Error is 60 minus 30, 30. Therefore, error is more than 10%. That's why 100% output. 100% output. Now, another tolerance is at 5%. That is 55. Another tolerance is 10%. That is 50 degree centigrade. So, whenever it crosses 50, the bandwidth comes here between 5 and 10%. That's why it is reduced to 75%. Now you can expect less overshoot. Because earlier in this region we have 100% output. Now it becomes 75%. Controller output is 75%. That's why the speed at which it increases, reduces. That's why we can expect less overshoot. After some time, when it crosses 55, error becomes in this bandwidth 0 to 5%. That's why further there is a decrease in slope. That's why it reduces. The slope is reduced further. If it is within the tolerance of 0 to 5%, up to 65, the percentage is only 50%. We can expect that it is within that 55 and 65. Suppose it exceeds 65 means we'll give only 25%. We'll give controller output becomes 25%. Suppose it exceeds 70. If it exceeds 70 means, suppose if it exceeds 70% means, then it becomes 0%. So we graded the controller output to 0%, 25%, 50%, 75%, 100% like that. How many points are there? How many points are there? The band of minus 5 to 10%. This is 1 point. This is second. This is third. This is fourth. So it becomes 4-point controller. 4-point controller. We can make 3-point also like this. But here, if it is 3-point, we can make 3-point also. 3-point means this is 0, this is 100. So here we'll make it 50%. 0, 50, 100. If it is within the tolerance, we are giving 50%. So say tolerance is 2%, minus 2%. If it is within that 2%, we'll give 50%. This is 3-point controller. 3-point controller. This is 4-point controller. 4-point controller. But ideal on-off controller is a 2-point controller. We made 3-point, 4-point. So if we increase the number of points, we can expect less overshoot. But again, it is wandering around set point. Never settle at set point. Never settle at set point, because we do not know the value for which it will settle at set point. We do not know. The controller do not know. Controller do not know. That's why it is not possible to make set point equal to PV. If we increase the number of points, suppose I am increasing the number of points like this. Every 5% I am having one increment. Why every 5% I am giving increment. So number of steps increased, 10 steps, 20 steps, 30 steps, so that we can reduce the overshoot. As the number of steps tends to infinity, it becomes the step will become like this. Am I correct or not? Number of steps tends to infinity means it becomes like this. Then it is called the proportional control. Proportional controller. So we are approaching the proportional controller from on-off controller. In on-off controller, how many steps? Only 2 steps. The wandering is more, deviation is more. It never settled at set point. That's why we made it 3-point controller. So 3 outputs instead of in on-off controller only 0% output or 100% output. Only 2. That's why there is a wandering around set point. To avoid that, we made 0%, 50%, 100%. We are giving 50% power input. So we can vary the voltage. So we can vary the voltage. If it is 100% means 220 volt, let us assume. 0% means 0 volt. 50% means 110 volt. Like that, we can vary the voltage. So further, some arrangement is there. So we can give 3-point control. Here, 4-point controller. We can give 25% voltage, 50% voltage, 100%, 75% voltage, or 100% voltage. 0, 25, 50, 75, 100. So 5-point, not 4-point. So 5-point control. 5-point controller. We can make a 10-point controller. In that 0%, 12 and half, 25, then 20 between 25 and 37.5, 50%, 67.5, 75%, then 87.5, 100%, like that. So we can give 10-point. That is also possible, so that we can reduce the overshoot. If that number of steps tends to infinity, it becomes straight line. Then it becomes proportional control. Proportional control. This is error. This is controller output. This is controller output M of t. What is the expression for this M of t? If step becomes slope, the slope, that is Kc. Slope is change in y upon change in error. That is slope of this line is Kc. Kc is slope of this line. Kc multiplied by E of t. Slope multiplied by error. If slope equal to 1, if error becomes 100, control output 100. If slope equal to 2 means, if error becomes 50, control output becomes 100. If slope is 25 means, if error equal to how much? Error becomes 4. The slope is 25 means, if error equal to 4, then it becomes 100. Then it becomes 100. So if slope Kc equal to 25 means, if error equal to 4, the controller output will be 100%. So that is called a proportional control. If error is more controller output. So on-off controller comes to proportional controller. If number of steps from 2 to infinity, then it becomes proportional controller. Can we expect a satisfactory output? That we will check now. What is steady state error? Now we want to reduce error because in an on-off controller it is wandering around set point. It is wandering around set point. We want to remove that wandering. We want to make set point equal to PV. For that we found a proportional controller, that is M of t equal to Kc multiplied by E of t. That is the controller output. Equation for the controller output is M of t equal to Kc by E of t. What is steady state error? Then G of S is multiplied by Kc. G of S is multiplied by Kc. Let us assume that G of S equal to K upon tau S plus 1. That is G of S. Therefore, on introduction of this controller, the transfer function becomes, this is set point, this is controller Kc, this is the transfer function G of S, system, there is a feedback, negative feedback, this is the output Y of S, this is input R of S, set point is given as R of S. What is the transfer function? we have to multiply these two. That's why Kc multiplied by K, the transfer function, forward transfer function, Kc multiplied by K. What is steady state error? E of S equal to what? E of S equal to 1 by 1 plus G of S H of S. Am I correct or not? We studied in control system. E of S equal to 1 upon 1 plus G of S H of S. What is the input? R of S. E of S equal to R of S upon 1 plus G of S H of S. What is E of infinity? E of infinity means final value. E of infinity means final value. Final value equal to limit S tends to 0, S E of S. Am I correct or not? Final value theorem. You studied final value theorem. That is S, limit S tends to 0, S E of S. Final value. E of infinity equal to, we can find directly from S domain, S tends to 0, S E of S. If you substitute this, what you will get? Limit S tends to 0, S R of S upon 1 plus G of S H of S. G of S H of S. For step input, suppose I am giving step input of unit step input. What is the input equal to what? R of S equal to 1. If I give R of S equal to 1, what I am expecting? Y of S must be 1. Y of S must be 1. Am I correct or not? If I am giving set point equal to 1 means output also must be 1. That is my expectation. So let us check. R of S equal to 1 means take Laplace transform for R of S. R of t equal to 1. That is step input. For a step input, if you take Laplace transform, that is 1 by S. If you substitute that, R of S equal to 1 by S, 1 plus G of S. G of S is K multiplied KCK divided by tau S plus 1. That is G of S. Unity feedback, that's why H of S equal to 1. S getting cancelled. S getting cancelled. Limit S tends to 0. If you substitute S equal to 0, what you will get is 1 upon 1 plus KCK upon 0 plus 1 or 1 upon 1 plus KCK. 1 plus KCK. The error equal to what? Error equal to E of infinity. Steady state error equal to 1 upon 1 plus KCK. It means what? After infinite time, there is a error. That is 1 by 1 plus KCK. 1 by 1 plus KCK. That is the error. It is not equal to 1. It is not error. Error must be 0. What we are expecting is after converting the on-off controller into proportional controller, we are expecting that the error becomes 0. But what we are expecting is error must be 0, but it is not happening because the expression for error, E of infinity, steady state error is 1 by 1 plus KCK. What value of KC error becomes 0? What value of KC error becomes 0? The expression for steady state error is E of infinity equal to 1 upon 1 plus KCK. For what value of KC, error becomes 0. Steady state error. For what value of infinity? Yes. So 1 upon 1 plus infinity, that is equal to 0. Therefore, KC must be infinity. Controller gain, if we make controller gain equal to infinity, then only the error becomes 0. That's why but practically it is not possible to give infinity controller gain. Practically it is not possible. That's why a proportional controller always gives steady state error. Proportional controller always give steady state error. This is mathematics. Mathematics says always steady state error will be there because KC never becomes infinity. KC never becomes infinity. That's why always there will be a steady state error. That steady state error is 1 by 1 plus KCK. The steady state error is 1 by 1 plus KCK. Always steady state error is there. This is mathematics. How to understand why proportional controller gives steady state error. What is M of t? M of t equal to KC multiplied by E of t. Controller output equal to what? Function of error. Can I write like that? Kc multiplied by E of t can be written as function of E of t. So if you want a controller output, means some error must be there. Then only there will be a controller output. It's not possible to create controller output without error. That's why error cannot be removed. I can remove error if you give me error means how I can remove the error. If you give me error, then only I can generate controller output, means that controller output cannot remove steady state error, because the controller output is function of error. That's why we cannot remove steady state error by proportional only controller. That's why P only controller always gives steady state error. P only controller always gives steady state error. Suppose I am taking a servo response. I am taking a servo response. The set point is this. This is the set point. Now the process is here. Present pros variable is here. Present pros variable is here. Now we change the set point. Now change the set point. If it is a proportional P only controller means it will increase, it will oscillate, and it will settle like this only. Always there will be a steady state error. Always there will be a steady state error. This is servo response of a P only controller. Servo response for a P only controller. Always there will be a steady state error. This is servo response. What is servo response? Servo response means we are changing the set point. This is set point old. This is set point new. Now I change the set point from 50% to 60%. Earlier it was 50%. Now it is 60%. So the controller tried to change from 50 to 60, but there will be a steady state error. Because proportional controller is function of error. That's why it's not possible to remove steady state error. If it is regulatory response, what happens? Regulatory response, let us assume that no controller, set point hold this, pros variable also along with set point, up to this point. At this point, some disturbance is coming into the process. That's why the process will deviate and settle here. No controller, no open loop. Because of open loop, it deviates. Because of disturbance, it deviates and settle at new value. So the error is how much? This is the error. And this much error. Because no controller. Disturbance came, that's why error came. No control. No control. Suppose I am introducing a proportional only controller. The proportional controller try to control, that's why it will oscillate and oscillates, and finally it will settle like this. What happens? P only controller, a disturbance is given, but without controller, a large error, but it reduced the error, but it never remove the error. It cannot eradicate the error. It cannot eradicate the error, but it can reduce the error. P only controller. This is response for P only controller. P only controller. Because controller output is function of error, that's why error is required to give controller output. That's why it is not able to remove the error completely, but steady state error is reduced. We will compare with no controller. With the proportional controller, it reduces. How we can remove error? How we can remove error? This is called, before going to that, what is the name for, another name for regulatory response? Load response. Load response or regulatory response. Load response or regulatory response. Here it is called servo response, set point change. In both cases, steady state error is there. In both cases, steady state error is there. We'll compare with no controller, there is a decrease in error. That's all. That only we can expect. How to remove error?